Hi, this is Shoikat Mujumdar. Our today's topic is Compton Effect, and the topic lies in the module Quantum Mechanics. The learning objective of this module is to acquire working knowledge of the quantum mechanics postulate on the physical systems. Compton in 1923 observed the fact that when X-rays, that means highly energetic photons, fall on some metal surface where there are loosely bound electrons, just like graphite, carbons, then electrons are scattered and photons also scattered. So there the wavelength of photon is increased. So this change is known as the Compton effect. This is the incident photon, then scattering of the photon with reduced energy, and the electron is also dislodged. Here this is the same picture. From the shell, photon is falling onto this one, radiation, electron is dislodged, radiation also scattered. When monochromatic beam of X-rays is scattered from a material, then both the wavelength of primary radiation, that is unmodified radiation, and the radiation of a higher wavelength, this is known as the modified radiation, are found to be present in the scattered radiation. Presence of modified radiation in scattered X-rays is called Compton effect. This is the incident photon of energy h nu, and its momentum is h nu by c. Electron is at rest. As it is rest, so its rest energy is m naught c square, and its momentum is 0. Now, when the photon is incident onto this one, then after the collision, the electron is recoiled along this direction with an angle of phi with velocity v, and the radiation is scattered along this direction with an angle of theta. So say now the reduced energy becomes E dash is equal to h nu dash. That means energy is reduced, so nu becomes less. As nu is less, then wavelength is increased, as frequency and wavelengths are inversely proportional. So if m be the mass of the recoiled electron, then its momentum is mv, its horizontal component becomes mv cos theta, and its vertical component is mv sin theta. If it is in negative direction, minus mv sin theta. Now photon, its momentum is h nu by c, its horizontal component is h nu by c, h nu dashed by c cos theta, and vertical component is h nu dashed by c sin theta. From the theory of relativity, total energy of the recoiled electron with V, as you know, energy is E is equal to mc square, which is equal to, total energy is E is equal to mc square, which is equal to kinetic energy plus its rest mass energy m naught c square. So kinetic energy is equal to mc square minus m naught c square. So putting the value of m is equal to m naught root over 1 minus v square by c square, it is relativistic mass. So k is equal to m naught c square by root over 1 minus v square by c square minus m naught c square. Taking common m naught c square, this becomes 1 minus root over 1 minus v square by c square minus 1. Similarly, the momentum of the recoiled electron is mv is equal to m naught v by root over 1 minus v square by c square. Now from energy calculation. From the conservation of energy before the collision and after the collision, energy will be same. So before the collision, energy of the photon is h nu. Plus after the collision, h nu dash, energy of the photon, and change kinetic energy m naught c square. As initially it has no kinetic energy, after the collision it has got the kinetic energy k, mc square 1 minus root over 1 minus v square by c square minus 1. From the conservation of momentum along x-axis, photon its momentum is h nu by c, y-axis it has no momentum, we have considered, is equal to, along x-axis the horizontal component of momentum is of the scattered photon is h nu dash by c cos theta plus this is h nu dash by c cos theta, and here recoil electron's momentum is mv cos phi. mv cos phi, we have to put the value of m is equal to m naught root over 1 minus v square by c square. So come to this slide. So this is cos theta for the scattered photon and this is mv cos phi. So putting this value, mv means m naught root over 1 minus v square by c square cos phi. And the vertical component, along this direction, along the vertical direction, incident photon has no momentum, but it has the scattered photon having h nu dash by c sin theta, and recoil electron has mv sin phi in the negative direction. So we have to put the value of m is equal to m naught root over 1 minus v square by c square. So this is equal to 0 of the before the scattering. After the scattering, h nu dash by c sin theta minus m naught v root over 1 minus v square by c square sin phi along y-axis. Rearranging and squaring both sides, the equation 2, we can write h nu by c minus h nu dash by c cos theta whole square is equal to m naught square v square by 1 minus v square by c square cos square phi. Now rearranging equation 3, this is from this equation, h nu dash by c sin theta whole square is equal to, and squaring also, and m naught square v square 1 minus v square by c square sin square phi. So adding these two equations, equation 4 and 5, we can write h nu by c whole square plus h nu dashed by c whole square minus 2h square nu dashed by c square cos phi is equal to m naught square v square by 1 minus v square by c square. Now from equation 1, h nu by c minus h nu dash by c plus m naught c is equal to m naught c by root over 1 minus v square by c square. This is the equation 1. This is the equation 1. From this equation, we have written this one. H nu by c minus h nu by h nu dash by c, dividing both sides by c, this is minus, then m naught c by this minus m naught c. So this becomes this. So m naught c in the right hand side, it comes to the left hand side, becomes plus. Come to this slide. On squaring, so from equation 1, we can get h nu by c minus h nu dash by c plus m naught c is equal to m naught c by root over 1 minus b square by c square. Squaring both sides of this equation, we will get h nu dash by c whole square plus h nu by c whole square plus h nu dash by c whole square plus m naught square c square minus 2h square nu dash by c square plus 2h m naught nu minus nu dash is equal to m naught square c square 1 minus b square by c square. Subtracting this equation, subtracting from equation number 6, come to this equation. This is equation number 6. We will get h nu by c whole square, h nu dash by c whole square. All these things will cancel out. This one will also cancel out. H nu dash. This one will taking common. So this one becomes 6. So h square nu dash by c square will be common. So this one becomes 1 minus cos theta. So this becomes, the equation becomes minus 2h square after the simplification. Minus 2h square nu dash by c square 1 minus cos theta plus 2h m naught nu minus nu dash is equal to 0. Now, after changing the sides, 2h m naught nu minus nu dash is equal to 2h square nu dash by c square 1 minus cos theta. So m naught nu minus nu dash becomes h, 2 will cancel out, this h and 1 on the h will cancel out, h nu dash by c square 1 minus cos theta. But nu is equal to c by lambda and nu dash is equal to c by lambda dash. So lambda dash is a modified wavelength and nu is the incident wavelength. So from this equation, as m is common, c by lambda minus c by lambda dash, taking common m naught c, this becomes 1 by lambda dash minus 1 by lambda. So here also c by lambda, c square by lambda dash. So come to this slide. So this one becomes m naught c 1 by lambda minus 1 by lambda dash is equal to h by lambda into lambda dash 1 minus cos theta. So this becomes m naught c lambda dash minus lambda by lambda dash is equal to h by lambda into lambda dash 1 minus cos theta. Cancelling out this denominator part. So lambda dash minus lambda is equal to h by m0c 1 minus cos theta. This change in wavelength is known as the Compton shift and we will represent it as delta lambda. So delta lambda is equal to h by m naught c 1 minus cos theta. So Compton shift only depends upon the angle of the scattering. This is scattering angle. It neither depends upon the incident wavelength nor on the scattering material. This term h by m0c is known as Compton wavelength and represented by lambda c. This h by m0c is known as Compton wavelength and represented by lambda c and its value is 0.0243 angstrom. 0.0243 angstrom. Experimental verification of Compton effect. This is the experimental setup. So monochromatic X-rays is produced from the molybdenum target of an X-ray tube are made to fall on carbon scatterer. It's a graphite. The corresponding lambda values are calculated using Bragg's law. The scattered X-ray is observed at the ionization chamber, or this is the X-ray detector. Ionization chamber, or known as a detector, X-ray detector, to measure its intensity. Compton found that the spectrum recorded after scattering had K alpha lambda dash line corresponding to lambda dash. That means modified line after the collision, which is on the longer wavelength side of the primary K alpha line corresponding to the lambda. He also observed that the change in wavelength, the modified light and the incident light, increased rapidly as the scattering angle is increased. As the scattering angle is increased, the change in wavelength delta lambda will be increased rapidly. The change in wavelength was independent of the incident wavelength. This is the experimental verification. Monochromatic X-ray is coming on the graphite target. Photon is scattered and it is captured by the Bragg's X-ray spectrometer. So when there is only the incident radiation, there is no collision, then this is the peak of the intensity of the X-ray radiation. When it is collided with the graphite target, when the scattering angle is 45 degree, then there are two peaks. This is the shift between these two. When it is 90 degree, this one to this one. When 135 degree, the shift is increased. So delta lambda increases with the increase in theta. Compton effect cannot be observed in visible light. Only light with higher frequencies produce Compton effect. The visible light, its wavelength range is only 400 to 780 nanometer. Now, we know delta lambda is equal to h by m0c 1 minus cos theta. That means 0.0243 1 minus cos theta angstrom. When theta is equal to 180 degree, so then cos theta is equal to minus 1. Minus 1 means this term becomes 1 minus minus 1, that means this term into 2. So 2 of this entry 0.0243. So multiplying this, the delta lambda will be maximum when 1 minus cos theta is maximum, that is 2. That is delta lambda max is equal to 0.0486, approximately 0.05 angstrom. So Compton effect can be observed only by radiation having wavelength of few angstrom. For lambda is equal to 1 angstrom, delta lambda is equal to 1%. For lambda is equal to 5000 angstrom, delta lambda is equal to almost equal to 0.001 angstrom. So this change in delta lambda is undetectable. So that's why Compton effect only visible with the high frequency radiations like X-rays, gamma rays, etc. With the visible light, it is not possible to produce. Already we have discussed Compton effect cannot be observed in visible light, but it can observe with the X-rays. If we take the calculation, wavelength of visible light say around 6000 angstrom. So energy of visible light is equal to hc by lambda. Putting the values of h, c and the lambda, that is 6000 angstrom, the energy becomes around 2 electron volt. But the binding energy of an electron in the atom is almost equal to 10 electron volt. For example, the binding energy of an electron for simple hydrogen is almost equal to 13.6 electron volt. So when visible light will fall on a target, it cannot liberate electrons of the scatterer. So we cannot see Compton effect with visible light. But the energy of an X-ray of wavelength, this is almost around 1 angstrom. This is almost around 1 angstrom. The energy becomes 2 into 10 to the power 3 electron volt. And for gamma rays, it is almost equal to 10 electron volt. So when X-rays or gamma rays will fall on the target, they can liberate electrons of the scatterer at rest. Hence, we can see Compton effect with X-rays or gamma rays. Another point to discuss, that is, the intensity of Compton lines depends upon nature of the scatterer. From the interpretation of primary lines, we know that the intensity of parent line is larger for heavier electrons than that of the modified line, while for lighter elements the intensity is lower than that of the modified line. Hence, only the intensity or energy of the Compton lines is dependent on the nature of the scatterer.